we look at the derangement problem. So what is that? That is a permutation of n elements where no element is at the original position. So in other words, for the permutation that has no fixed points. Yeah. So we introduce this notation here, sometimes called sub-factorial, and is related to the regular factorial here with Euler constant. And this operator is the integer operator, right? And there's recurrence relationship here. So we're going to study all that today. Okay, before we get lost, let's start with some simple example. Yeah. So one example here, that is the problem when it was first raised back in 1600. So the question is, I have a bunch of letters I want to put into the envelopes. What is the chance that every letter is put in the wrong envelope? So in this case, what we do is we number envelope 1, 2, 3. Yeah, and for the 6 different permutations of 1, 2, 3 letters, and we're going to care about the derangement. In other words, low letter is at the right envelope. So in this case, we have to remove the first 2 because 1 is at the right place, and we have to remove this because 2 is at the correct place, and remove this one, 3 is at the right place. The remaining 2 is called derangement because nobody is at the right envelope, right? So here we have 2 cases. So in this case, we say the notation here is like for the three objects, right? And the number of derangement is 2, or sometimes we use notation d sub 3, right? Equal 2. Okay, so the notation could be this one, or could be d sub n. Yeah, that is the number of derangement with n distinct elements. Okay, so how about n equal 4? So what is d4? For that, we could just enumerate, right? So if the envelope original position is 1, 2, 3, 4, for the derangement and in the first position, you cannot put 1, you have to put either 2 or 3 or 4, right? So if you put 2, now here you can put 1, 4, 3, and you can put, let's say 3, 4, 1, and you can put 4, 1, 3. I don't think there are other ways. Yeah, so let me see those. All right, so by symmetric property here, you would have 3 other entries here. Total would be 9 entries, right? So this number of arrangement here. So let's enumerate them, right? 1, 4, 2, 3, 4, 1, 2, and 3, 4, 2, 1. For the 4, you also have 3 cases here. Let's write them down here. 1, 2, 3, 3, 1, 2, and 3, 2, 1. All right. So those are 2 examples. So the d4 in this case would equal to 9. All right. How about other cases? We're going to look at the recurrence relation for d sub m. For a bigger number n, we're going to try to figure out d sub m through the recurrence relationship. Okay, let's do some analysis here. Now this time we have n envelopes. Now assume in this case for the envelope number 1, right? So it cannot contain letter 1. It must contain letter I, where I is not equal to 1. Okay, so how about other envelope and letters, right? So there are two cases here. Case 1, let's look at the i's letter. Where does it go, right? Not the i's letter. I's letter goes to 1, right? The first letter, right? This is a letter. Now, if it goes to I, in other words, what we have is the remaining, n-2 envelope and the remaining n-2 letters. So that's gonna be n-2 letters and n-2 envelope that is left, right? So that is a subproblem of D sub n-2. So there are that many ways of derangement. So if you have case number 1 where letter 1 goes to i's envelope and letter I goes to envelope 1, right? So you just take these two out and your remaining is like another problem, which is the n sub 2. That's straightforward. How about the second case? The second case where you have I goes to, let's copy this, right? Let's copy this here, paste it here. Yeah, so what do you have? In this case, you don't go to I. The letter 1, you don't know where it goes, and here you may have other cases. So what we do is, so this is fixed. Yeah, this one, envelope 1 contains letter I, but envelope I contains something that is J, right? And J is not equal to I. So when you think about it, you're gonna have, since this envelope 1 is already has a letter, so we look at the remaining n-1 envelopes. Okay, so we have n-1 envelope, and we have the remaining, what are they? That is 2, 3, and go to n, right? And I is in the middle here somewhere. And you also have n-1 letters. What are those? Because letter I is taken, so you're gonna have letter 1, yeah, letter 1, 2, and you don't have I here. I is gone, yeah, you don't have I, and you have n. The total n-1 letters. And the rule here is that letter 1, yeah, letter 1 cannot go to letter I here. Why? Because if that is the case, that belongs to case number 1. So we're looking at case number 2, right? Okay, so think about it, right? If you rename this letter 1 into I, right? Let's call this I. So, and you put it here, right? Because this is a problem with n-1 envelope and n-1 letters, and I, which is letter 1, by the way, of the original problem. In this new problem, I, letter 1 was the original one, it cannot go to I, right? So in this new problem, of course, I, by definition, you cannot go to your envelope. You must go to any other envelope. It's fine. So that is, you have n-1 envelope with n-1 letters, and the total derangement is going to be dn-1. Okay, so what is the relationship now? If for the letter 1, right, it contains I, but then of course that's only one of the cases, because this I here, for the n float 1, it could be n minus 1 choices, right? This I could equal to 2, equal 3, and equal m. So in summary, d sub n, right, is going to be dn minus 1 plus dn minus 2 for the case where letter I goes to n float 1. But since we have many other cases, yeah, how many other cases? We have n minus 1, because letter I could take a value from 2 to m. Okay, so that's the recurrence relationship we are talking about. Okay, so with that, let's try it out. Earlier we know that d3 equal 2 and d4 equal 9. So what is d5 for the 5 element, right? So that's going to be, you're going to have summation of the 2, which is 11, and then you're going to times n equal 5, that's going to be 4, yeah, and that's n minus 1, right? So and that's equal 44. Now how about d6? Yeah, so that's going to be 44 plus 9, that's 53, right? So 53 and times 5, yeah, so that's going to be 265, getting bigger. Okay, so now in general, can you have a equation for dn? Because right now you only have the recurrence, right? So what we can do with this recurrence, we can solve it, right, by rewriting it. Okay, we can rewrite this recurrence here by moving n times this term to the left hand side. So let's do that. So that's going to be dn minus n dn minus 1. On the right hand side, you still have negative 1 dn minus 1, and you have n minus 1 times dn minus 2. Alright, so let's rewrite it as negative dn minus 1 minus n minus 1 dn minus 2. Yeah, so what you can do until you get negative 1, because each time you have negative 1, right? And eventually you can say d2 minus 2 d1. And this is going to be how many times? It's going to be n minus 2 times, right? So from dn to d2. So each time you have a negative sign here. Yeah. So what is d2? Earlier we know that d2 is actually, for the 2 elements there's only one way, for 1 element there's no way, right? So that's 0, that's 1. So the whole term is, this is actually 1. So this is going to be negative 1. And for negative n minus 2 is equivalent to n, right? Yeah. So either negative or positive 1. So that's another important recurrence we have. Let's write it. Okay. So in other words, dn minus n dn minus 1 equal negative 1 raised to the nth power. So that's another relation that we got. Okay. Now, still, we need to do further, right, in order to get an expression for dn. So what you do here is we try to use telescoping, okay, by dividing n factorial on both sides. So what we have is, so dn n factorial, and here n dn minus 1 n factorial, this cancels and then becomes n minus 1 factorial, right? So let's erase that. So it's going to be n minus 1 equal negative 1 m and n factorial. Now that's telescoping coming. So you're going to rewrite this equation here, right? For n and n minus 1 here. You're going to have n minus 1 factorial minus, that's going to be n minus 2, yeah, telescoping. And that's going to be negative 1 n minus 1 and n minus 1 factorial. And then until you have another one at the towards the end, what we want to do is we have d2 2 factorial minus d1, and that's going to be 1 factorial. That's equal to and n equal 2, right? So that's going to be 1. That's going to be 2 factorial. Okay. So for all that, you're going to add them together, right? Do the add, and what you're going to have is this term going to cancel, that's going to cancel, this is going to cancel, and then you only have this term, and here you're going to have summation on the right hand side. So what we have is expression for dn. So the dn, yeah, over n factorial minus d1 earlier, we know that is 0. So equal here is going to be summation from what? From 2 factorial minus 3 factorial. This is going to be 1 because this is alternating terms, right? They're going to be plus, that's going to be 4 minus, and until you at the end you're going to have negative 1 raised to nth power n factorial. Okay, so that's the expression. So what is dn? So dn is going to be n factorial times this whole term. All right. So this whole term, if you learn calculus here, you may recall the expression, the Taylor series or Maclaurin series for e to the x power, right? So let's review that. So e x, yeah. So that one is going to be 1, yeah, 1 plus one factorial plus x squared 2 factorial plus so on and so forth, right? So if you plug in x equal negative 1, you know this is 1 over e, that's going to be 1 minus, 1 over 1, yeah, plus 2 factorial, this is going to be 1 minus 3, and so on and so forth, right? And this goes forever, so this cancels, and the term here is exactly the same here. Okay, so here now usually if we only keep the finite terms, right? Yeah, so you can say that's equal some finite terms until negative 1 and over n factorial plus the remaining one you can consider as arrow term, right? So this is the remainder time, not this big R. Just say the remainder time has some values here, right? So of x. The idea is that as n big enough, that's going to be some value that is small, we can ignore, okay? So what we have is, here, let's finish the term here, yeah? Over here, the right hand side, you can say this is going to be 1 over e and minus some remainder term, yeah? This remainder term is just going to be n is big enough that can be ignored. So it turns out that we can have a formula here is n factorial divided by n could be a fraction, but then we put integer here, yeah? This means closest integer to this fraction here because there is remaining term in the sequence. So that sometimes if you do the floor function, that would be n factorial over e plus 1/2 and then put a floor function here, okay? So that's what we derived here, okay? Now, how accurate is this? Yeah, let's try a few different numbers here, okay? So we use computer program to calculate this number here, right? This term here, we're saying that it's going to be a fraction because there's a remaining term here. So if you take an integer, it's going to be 0. And for number 2, because closest integer is going to be 1, so that's 1. And for 3, d3, we know that d3 equal 2, d4 equal 9. This is 8.83. Round up to integer would be 9. And 44, this all matches with earlier results, right? Earlier we have 265 up to 65, right? And this number getting bigger, and of course the closest integer here, this is going to be round up to 9, yeah? So that's matches what we derived earlier, yeah? So this is the main result for today. Now for this relation here, for this another formula here, right? For this one, there is another interpretation of this. We can derive this formula using what is called Inclusion Exclusion Principle of counting, a common technique in dealing with counting problems. But we're not going to cover this today, so we're going to cover it next time. All right. Thank you for your time. Hope you enjoy this video. Please subscribe to the channel.